All right, what we're doing today is in this section we're going to be solving equations that have trigonometric functions in them. Before we jump in with the trig equations though, I want to do a quick review of college algebra. Super quick, short example kind of review. If we have a linear equation, we know that we're going to try to work using addition and subtraction to get the x's on one side of the equal sign and anything without an x on the other side. Once we have separated variables from constants, then we'll multiply or divide both sides by the coefficient to get the x by itself. When we're in trig, in this chapter and beyond in your other math classes, we have to be able to see the bigger picture of things. Understanding how to solve a linear equation is important, and hopefully you guys could do those two steps maybe even all at once in your head. But understand that anything of this form, of the same sort of pattern, can be treated and solved using these same methods. Okay? They may not be polynomials. They may have radical expressions in them. They may be rational functions, or maybe they have trig functions. Maybe they have trig functions in them. Let me find. Okay, I lost my examples, but I found them now. Maybe I have something like the square root of 3 times the cosecant of x minus 2 equals 0. Okay. Now, yes, our goal is to solve for plain old x and get x equals some value in radian measure. But also, if we look at this and treat this, this meaning in the box, as our variable, you could do a substitution if you want to say square root of 3 times u minus 2 equals 0. You can. But initially we want to solve for cosecant of x. Okay, so this is like the linear equation that we have on the other page. It's been a long day already. Okay, first by adding 2, and then we'll divide both sides by square root of 3. Okay, so our first step is to get cosecant x by itself, or sine x, or cosine x, or whatever trig function happens to be there. Okay. Then if we, from here, then we'll actually figure out what angles make this true. Okay. Since the cosecant is the reciprocal of the sine, a lot of us would much prefer to look at things in terms of sines and cosines and tangents versus the cosecants, so the secants, cotangents. So if 1 over sine x is 2 over square root of 3, that means sine x is square root of 3 over 2. Okay, show the algebra steps if you need to. Okay. Now, in the directions, if they just say solve for x, okay, let's solve this equation for x, and they don't give us any restrictions on the domain for our values of x, then this is actually going to have an infinite number of solutions. So first and foremost, we have to figure out what the two solutions are between 0 and 2 pi, because we know that the sine function is positive in 2 quadrants, and the sine function is negative in 2 quadrants. So the sine of x is equal to the square root of 3 over 2 when x is equal to pi over 3. Okay, that's our first quadrant answer. We also know that the sine function is positive in quadrant 2, and so a pi over 3 reference angle in quadrant 2 looks like 2 pi over 3. But because the sine function is periodic, because it is a period of 2 pi, then I know if I add 2 pi to pi over 3, or 4 pi, or 6 pi, or 8 pi, okay, that would also be a solution. Or if I subtract 2 pi, or 4 pi, or 6 pi, or 8 pi, that would also be a solution. Same thing if I add or subtract a multiple of 2 pi to 2 pi over 3, those would all be solutions as well. So I know if I add 2 pi, or if I add 2 times 2 pi, or 5 times 2 pi, or negative 3 times 2 pi, then I'm gonna be at another solution. And so the way we write that generic infinite number of solutions is we say 2 pi n, or 2 n pi, wherever you want to put the n. And because if n is 1, then I'm adding 2 pi. If n is negative 1, I'm subtracting 2 pi. And so here is my list of solutions for that equation. Okay, there's an infinite number of solutions. If I just say pi and 2 pi, pi over 3 and 2 pi over 3, that's not enough. Those are the ones between 0 and 2 pi. But if they said find all of them, then I need to include the period and say if I add or subtract a multiple of 2 pi from these values, I'd also be at a solution. So next, maybe I have 3 sine x plus 1 equals sine x. Again, I'm thinking initially anyway as the sine x is my variable. And so that's like saying 3x plus 1 equals x, okay, or 3u plus 1 equals u. And so I know that when I have x's in more than one place in my equation, I didn't here, but if I had x's on both sides, I would try to get them together by adding and subtracting them. I would also try to get anything without an x in it to the other side to get it away from what I'm working with. Okay, so I could subtract in black. Subtract 3 sine x from both sides and have 1 equals negative 2 sine x. Then if I want to solve for sine x, I divide everything by negative 2 and say, now I'm in charge of figuring out when is the sine function equal to negative 1/2. So I know the sine is 1/2 at pi over 3 in quadrant 1. Okay, that would be positive 1/2. That's a lie. It's pi over 6. My mouth's working too fast this afternoon. Okay. But if I need sine to be negative 1/2, then I'm in which 2 quadrants? Okay. I want to pause so that you guys think these things through. Okay, sine is positive in the first 2, so it's negative in quadrants 3 and 4. So if I have a pi over 6 reference angle in quadrant 3, that'd be 7 pi over 6. If I have a pi over 6 reference angle in quadrant 4, that's 11 pi over 6. Again, because the sine function has period 2 pi, if I add or subtract any multiple of 2 pi to 7 pi over 6, or to 11 pi over 6, those are also going to be solutions to my equation. Okay, so being able to find the 7 pi over 6 and 11 pi over 6 is very important. But then don't forget that if you're finding all solutions that you have to add, you have to take the period into account and add those multiples of 2 pi to each of those as well. Okay, I think those are the only 2 linear examples. Well, there's another one, I guess. But I'm going to come back to it in a little bit, okay, when we change the angles.